questions? Excuse me. Are there any questions about this example? Okay. All right, let's keep going then. So, from the deck of cards, what's the probability of drawing a -1? That is, what's the probability of drawing a card that has a -1 on it? Well, if we go back to what a deck of cards consists of, right? From each suit, each of these 4 suits, right? There are 13 cards. The cards are numbered from 2 through 10. There's also a jack, a queen, a king, and an ace in each suit. Well, are there any cards labeled -1? No, there aren't, right? So what would the probability be? Well, how many ways can we draw a -1? There's 0 ways of that happening. Well, if there are 0 ways of that happening, the probability should be a 0, right? In other words, it's impossible for this to happen. And since this event is impossible, the probability should be 0. So an event is called impossible. It's an impossible event if it has a probability of 0. And also, if it has a probability of 1, we say the event is a certain event. And any other probability is between 0 and 1. I think I forgot to mention that earlier, and I apologize for that. Probability is always a number that's greater than or equal to 0 and less than or equal to 1 by definition. Okay, so it's not going to make sense to say a probability of an event occurring is 2. That wouldn't make sense. Also, I wrote this down before, but I wrote it here again, that events, we use capital letters to denote them. We use capital letters to denote them. So again, if E is an event, the probability of it is denoted by this. I mean, I don't know if you guys know, I don't know if people here know set theory or not, but actually an event is a set, but that's a different story. Okay. Well, let's keep going then. So again, let's go back to rolling a 12-sided die. Again, it's a fair die unless stated otherwise. So what would the probability of rolling a 3 be? Well, again, all the outcomes in a 12-sided die are equally likely, right? I mean, we saw the sample space already, right? Let me get back to it actually. Now here, this is the sample space, right? So what's the probability of rolling a 3 or rolling any of these numbers? It would be 1 out of 12 because they're all equally likely. So the probability of rolling a 3 would be 1 out of 12. What's the probability of rolling a 5? Same thing, it'd be 1 out of 12, right? Because again, all the outcomes are equally likely. What about rolling a -3? Well, can that happen? Well, if we go back to the sample space, we can see, no, it can't. You know, we can't roll a -3. So that would have probability 0. And for even numbers, that was the next question. How many even numbers are there? In other words, what's the probability of rolling an even number? Well, we have how many even numbers? 1, 2, 3, 4, 5, 6, 6 even numbers. So there are 6 ways we can roll an even number. There are 12 outcomes altogether in the sample space. So the probability would be 6 out of 12. So it'll be 6 out of 12. So these are just some probabilities. Okay. All right, let's keep going then. Are there any questions on this? All right. So now this one's a little bit different. Let's suppose we roll, so we're back to a standard 6-sided die. What would the probability be of not rolling a 2? I mean, I know it's down there, but even on the slide that is, but even if it wasn't there, you know, how would you get it? The probability of not rolling a 2. Well, if you're not going to roll a 2, you have to roll something else. And what else could you roll? You could roll a 1, a 3, right? The sample space is here. A 1, 3, 4, 5, or 6. You know, anything else. To not roll a 2 means to roll any of the other outcomes. Oh boy. So to not roll a 2 means to roll any of the 5 remaining outcomes. So the probability there would be 5 out of 6. 5 out of 6. Now, what is the probability of rolling a 2? Well, I think we already saw that it's 1 out of 6. Now, what if you were to add these up? That's what I'm doing here. You'll notice that when you add, right? Again, when you add you have a common denominator, right? You only add the numerators. So what you actually get is 6 out of 6, which is 1. So in other words, this sum, the probability of not rolling a 2, the probability of rolling a 2, you add them up, you're going to get 1. Well, that's no accident. That's no coincidence, that is. Yeah?
Can you go back? Yeah. I don't understand the last.
Louder?
I don't understand the last point. Like, why would you add the non?
Why are we adding these?
Yeah.
I'm just illustrating that if you add these two, you're going to get 1.
Oh, okay.
That's all.
Thank you.
You're welcome. Good question. So she just asked that, you know, why am I adding these? Again, I'm just showing that if you were to add these, we're going to get 1. And that's actually no accident because of the next slide, of what's on the next slide. The complement of an event is basically that the event does not happen. So the complement of the event, rolling a 2, would be not rolling a 2. If you're drawing a card from a standard deck of 52 cards, the complement of the event, drawing a king, would be not drawing a king. You know, drawing one card at random. This is actually notation for the complement. It's the event letter, the event notation, but you put a bar over it. Right? And just like with rolling a 2, its complement, not rolling a 2, the sum of the probabilities is always going to be 1. It's always going to be 1. So for any event, if you take its probability and add the probability of its complement, you're going to get 1. And so, of course, from there, it follows that the probability of the complement is 1 minus the probability of the event, or the other way around. Actually, no, let me say it again. No, what I meant to say was, if you know, I mean, here you can calculate the probability that an event does not happen. What this really gives us, though, is if you know one of these two, you can easily calculate the other. Now, you might be thinking, why do we care about that? Sometimes one of these is easier to get than the other, depending on the experiment. But again, if you know one of them, you know the other. I mean, intuitively, this is what should happen because an event's going to occur or an event's not going to occur. You know, that's for certain. You do an experiment and a certain event can either occur or not occur. So, I mean, that's not a proof, but, you know, it's the idea behind it.